completeness theorem. Okay, so in the previous lecture I talked a bit about the real numbers, but some of the properties they have, and in the lecture, and sorry, in the notes you have more details about that. And if you were students in a math degree, you would have gotten to the reals or defined the reals in a rigorous sense, and so that you would have seen that the reals have a very important property that's called completeness. The reals are complete. Okay, and there are many ways to kind of reach that property, but one of them is to use this what we call the completeness theorem, kind of similar to this complete action, if you want. Okay, so that's not important, just that kind of the nerdy background of this, but you know, the real numbers have a very important property, is that they are complete. Okay, and this property can be expressed in this theorem. Okay, this theorem is the completeness theorem, and it says that suppose A is not a subset of R. Okay, just like before, A subset of R, and let it be non-empty. So A has some elements. Okay, this is the empty set. So the empty set would be the set that doesn't have any element. Okay. Well, so A has at least one element. Well, then these two properties are true. The first one is the supremum property. If A is bounded from above, then it has a supremum. And the infimum is properties that if A is bounded from below, then it has an infimum. Okay? So for instance, if we have the set A is the set of all real numbers such that x squared is smaller than 3. Okay? So if you think about the function x squared, okay, so this is A is the set of all real numbers such that the x squared, the value squared of x, is smaller than 3. Okay, so if you paint the parabola x squared, that, and this is 1, 2, 3, then A is the set of all numbers that lie in here. Okay, excluding this, which would be the square root of 3 and minus the square root of 3. Okay, so you could rewrite this like this: x in R such that x is greater than minus square root of 3 and smaller than square root of 3. Okay, and there's no smaller, greater or equal than, or smaller or equal than, because square root of 3 and minus square root of 3 do not fulfill this property. Okay, so the upper bound, so you can think of, you know, upper bounds for this are, you know, 10, you know, 100, whatever. But square root of 3 is an upper bound of A, and actually this is the supremum of A, because there can be no smaller bound. If you think about it, if you pick any number that's just smaller than the square root of 3, then it fulfills this condition, and that number will belong to A. But this number is the smallest of the upper bounds that is greater than every other element of A. Okay, but it doesn't belong to A, so this is not the maximum of A. And with the same argument, we can say that the minus square root of 3 is the infimum, and it's not the minimum of A. Okay.